Okay, now let me continue these sections. So I will give you some more examples. But before the examples, let me just give you some slight introductions on what we have here. Is if we have this kind of situations when the functions or the curve, we see that we have two curves, f and g, but in some intervals f is on the top of g, but in another interval we see that g is on the top of the f. So we could describe this f and g. Okay, now we could write down this as in absolute value. So this absolute value means that some part of the f is on the top and some part of g will be on the top. And of course, this is when f is greater or equal g, when g of x is greater than. Okay, and then we could describe this, the area of the between these two curves, as integrations from the interval a to b of this absolute value f of x minus g of x and then dx. Okay, so this will describe how it's the when. So sometimes when f is greater than g, we could write that, and when g greater than f, we could also write that. So we could have several integrations that we can separate from this. Okay, and I think I can give you as an example later. Okay. Okay, now let's see how the example will be. So I think the best way to see this example is with the trigonometric curves, as in the. Okay, if we want to find the area between these two curves, y cosine x and y sine x, from the interval 0 to pi over 2, we would see that it has two regions, a1 and a2, and we could take that as the area from 0 to pi over 2, as in the absolute value of cosine and minus sine. And this could describe a1 plus a2. Okay, and as you may see that we have another observation that this a1 and a2 is divided by this pi over 4. So we could describe this integrations and separate these two and take the pi over 4 as the interval. So the first one is the cosine is on the top, right? So we say this is our first integrations, and we need to plus the other integrations, that this is sine x minus cosine x dx. Okay. And we could solve this and say that this will be sine x plus cos x, right? Because minus minus, and plug in this, and also we could plus the other one. This will be negative cos x minus sine x from the pi over 4 to pi over 2. Or we could write this as in this. Okay. So if we plug in and try to compute that, this will be equal to this. Okay. But if you see clearly that the a1 and a2 is symmetric, right? So we could take the area as twice of the 0 pi over 4 cosine x minus sine x dx, and this will be 2 sine x plus cosine x from 0 to pi over 4, and this will be 2 1 square root of 2 plus 1 square root of 2 minus 0 minus 1, and this will be equal to yeah, the same, 2 square root of 2 minus 2, right? Okay. Okay, let me give you more examples how to solve the area between curves. Okay, so let me start with I think we can start with the area between the, so find area between line y equal x minus 1 and parabola y squared equal to x plus 6. Okay. Now if we take careful looking at these equations, especially the parabola, this parabola having y squared, so which means that the parabola is better to describe as in x, right? X equal y, right? So we could write that the 2x is y squared minus 6, or x is half y squared minus 3. Okay, we could describe this in the picture, and also we could describe the line in terms of x. Okay, so let's sketch this too. So this is our picture, and it's already mentioned the intersection, which is 5 and 4, -1 and -2 for each x, y. So if we want to get these numbers, we could start with taking these two and equaling both of them. So half y squared minus 3 equal y plus 1. And we could start with this. And then we could multiply by 2. And we could see that this will be y. And this is y equal 4 and y equal -2, which is correlates with the picture here, right? So that is how we find the intersections. And then we could solve this in terms of y. So the area is from now -2 to 4. Okay. So we could imagine with taking the rectangle as in this dy. So dy is here. So we could see that the height now it's this one, right? The height. So you can think that rotating this curves, and you will see that it's actually the same thing as we did before, which is the top equation minus the bottom equations. Now the xr minus the xl, or the right equations minus the left equations. Okay, now we could write down that the right equations, let me write down all this stuff, and this will be equal to, so this will be y plus 1 minus half y squared minus 3. And then we just integrate as usual. So this will be, or let me just directly integrate this. So y is becoming half y squared. Or maybe just compute first to give you more understanding. So 1 plus 3 is 4, and this will be dy. So the area is y cubed, and then plus 4y, and from -2 to 4. So area is taking all the numbers. Oh, this should be not 1/2, 1/6. Sorry. So this will be 64 plus 8 plus 16 minus, and then the -2 we put inside. And carefully calculate all of this. This will be equal to 18. Okay. So this is one example for the finding area between curves and using dy. Okay, using dy. Now let me go through another examples that might be useful, and we up until now we just have a direct results. So you just take the top equation minus the bottom equations, dx or dy, and then you get the direct results, and you can compute the integrations easily, right? So what if we need to take some time to observe the graphs, observe the area between the curves, and maybe we need to separate each area, become several parts. Okay, that's also a possible question. Okay, so let's start doing that. Okay, so the next example, let's see if we have this. Okay, the area. The area is between the curve 1 over x, y equal x, and y equal 1 over 4x. Okay, so so this will be the area. Okay, so what do we need to start with? Okay, so if we would like to solve this, then we need to imagine what kind of sample, rectangle sample, inside this area, inside this region, and we need to always think from that sample before we try to formalize our integrations. Okay, what I mean is we need to decide, like for example, if we need to take it into this dx, like this rectangle. So we need to decide, okay, if this is what we have, then we need to decide which is our curves that we need to take our height, right? We have height and dx. We need to take this area, right? So the height, okay, I think from 0 to some points over, well, if we look at this point, the intersection when x equal 1, the curve is changing, right? The curve is changed. So from y equal x, and then it's become 1 over x, okay? So the top equation is changing, which means that if we need to take this, then we need to take this area and divide by 2. So we need to take that as a1 and a2. Okay, let me put another graphs. This will be a1 and a2. And we need to state in terms of dx because of this, because we take this rectangle as our sample. So let's start doing that. Okay. So a is a1 plus a2, and then a1 is integration from 0 to 1, and then the inside one is x minus 1 over x, 1 over 4x, sorry, and then the x, and then plus from 1 to 2, the integrations is 1 over x minus 1 over 4x, okay, and then the x, and then try to solve this. And I think we can solve each one. So this one is becoming 3 over 4, right? 3 over 4x. So it's becoming 3 over 8 x squared from 0 to 1 plus. Now this part becomes ln, right? And then minus 1 over 8 x squared from 1 to 2. So first we get this is 3 over 8. Okay. And then plus this is ln 2 minus half, and then minus ln 1 is 0, and minus 1 over 8. So we have plus 1 over 8, and we have here is negative 4 over 8, right? So we have negative 3 over 8. And then this will be cancelled with this, okay? So we have the ln 2 as our results. Okay, that's the first case. The second case is we can also, taking this point here, let me write with the green color, and make another different area. So we could also make this 2 area if we take the sample dy, the rectangle dy, the small rectangle dy. So we take that as in this picture here. Let me make it more clear. Let me crop this. Okay. So if you see, we have also another a1, a2, and now we need to describe in terms of y. So all the equation we need to change. Okay, so you could also solve this problem within the terms dy. So a1 plus a2, so 0 to, and then you need to also find the intersection, of course. Okay, so 0 to 1 over 2 of the 4y minus y dy plus from half to 1 of 1 over y. Remember, the right minus the left. Okay, so 1 over y minus y dy. Okay, now this will be 3y. So 3y is 3 over 2 y squared from 0 to 1 over 2 plus this will be ln y minus half y squared from half to 1. So this will be 3 over 8 plus this will be 0 minus 1 over 2 and then minus ln half minus 1 over 8. So this will be minus 4 over 8 plus 1 over 8 is minus 3 over 8, so we can cancel all of this. So we have minus ln 1 over 2, and this is equal to, remember that ln, the half is 2 with power of negative 1, so this is equal to the ln 2. Okay, the same results. Okay. So either dx or dy, we could try, and it's up to you which method or which your preference, which one is your preference. This results will be the same. Okay. Okay, another example. Let's try to find this area here. Okay, you can stop the video and check the answers later. Okay. Okay, I think we can start. So we have this area in between the curve y squared minus 4y, and then the other curve is 2y minus y squared. Of course, we see the curves already, and it turns out that it's in the y terms, all the conditions. And it seems that when we see the drawing, the curve itself, it's kind of an obvious choice if we take this as our rectangle, right? So take this as our rectangle. So we take dy. So which means that we are going to take a is equal, we take it from 0 to 3, and we are going to minus the 2y minus y squared minus y squared minus 4y. Okay, and then we could write down minus 2y squared dy, and then this will be 3y squared. Okay, I think that is okay, and then solve it. This is 27 minus what is it, 9 and 8 is 18, so we have 9. Okay. I think it's simple. Okay, simple. Okay, how about the next one? Okay, let me go through. Okay, I think we can start to write the equations. We could start with so this is the boundary of the region. So we could have y equal cosine x, y equal e to the x, and x equal pi over 2. So all of this is the boundary. So can we solve this, and can we also sketch this first? So first of all, we could think, I believe we start from, let's say, drawing the cosine. Okay. Cosine, we start from this, let's say it's 1. Okay. And then let's say this is pi over 2, maybe pi over 2 or a little bit here. And then we go by and taking that root. Okay. And then we're taking this line as pi over 2. That's our boundary, right? And of course the e to the x, it will go through this 1, right? When x is 0, y is 1, right? For this part here. When x is 0, y is 1 for e to the x. So it should be start from here, we could see. And perhaps it goes through like this. And the area will be here, right? And I think it will be an obvious choice if we take the rectangle as this one. So we are going to have dx, okay? So we are taking the area as we moved from 0 to pi over 2, the e to the x minus cosine x dx. This is what we are going to compute. So we are going to compute this e to the x minus sine x from 0 to pi over 2. And this will be equal to e to the pi over 2 minus 1, right? And then minus 1 minus 0. So we have e pi over 2 minus 2, right? Okay, seems I think not too complicated. Okay, now let's see another one. Okay, I think we could take, I think, 2 more examples. I think it's okay. Okay, let's say we have the boundary is x 1 minus y squared, and x is y squared minus 1. So to begin the computations, we start with the, I think, y squared minus 1. So y squared is like this, right? But it's minus 1, so we need to shift it. We need to shift it to the right 1 unit, maybe there. Okay. And then we could draw like that. And let me just fix this. I think that's okay. And then another 1 minus y squared. Minus y squared is the, we mirror this through the y-axis, and then plus the 1 unit, right, to the left now. So it's supposed to be like that, right? Supposed to be like that, but we plus 1. So we are going to take the, oh wait, this, not this one. So sorry, this should be going to be here. Okay, I think going to be here, sorry. Yeah, and then the other one, the 1 minus y squared is over here. Okay. Because we treat x or y in x, right? I think this should be okay. Let me just make it okay. So this is the point, the vertex. Okay. So this will be the area. And if we look here, we see that this could be the rectangle, right? Our rectangle. So we could say that we are going to have the dy. First, we need to find the intersections to make sure the point. So intersection is when 1 minus y squared is equal y squared minus 1. So we say that 2 minus y squared is, 2 minus 2y squared is equal to 0. So we say that 2, 1 minus y squared. So y squared is 1, so y is plus minus 1. So y is plus minus 1, which means that we have negative 1 here and 1 is here, right? And we could directly compute area. So the right one minus the left one. And then we could say that because it's symmetrical, we could say this twice of the well, we could say for starter, we could say it's twice from right? It's twice, and then it is also twice from if we take it from the 0, right? So it's actually, we could see it's a 4 area. So we could say that it's 4 times the 1 minus y squared from 0 to 1, right? So we could say this is 4, and we take integrations. So it's 4, 1 minus 1 over 3. Oh, this is 8 over 3. Okay. Okay, let me go through another example. Okay, region enclosed by okay, let me check the questions first. Okay, I say we have the x cubed, y equal x cubed, and y equal x. Okay, and I think it's not too difficult to draw, so we could start drawing. So y equal x, just a line like that, and the y equal x cubed is going to be like that, one point like that, and the other point like that. Okay, so yeah, we could take the rectangle. I think this one should be okay, and then we could confirm that this A1 and A2 they are equal, right? They are equal. Okay, so we could take that as in the symmetrical. So we could take the area. Oh, before we take the area, maybe we need to make sure the intersection. So always make sure the intersection if it's not mentioning in the given information. So we need to take this equal to this. So x is equal 0 and x squared equal 1. So x is plus minus 1. So this will be 1, right? 1, 1. And this will be negative 1. So this will be negative 1, negative 1. Okay. So the area is twice, because of the equal of A1 and A2, they are equal. So 2 multiply with the integrations from 0 to 1 of x minus x cubed dx. So this is half x squared. This is 1 over 4x with the power of 4. This is 0, 1. So 2 half minus 1 over 4 is half. Right? It's 1 over 4. Yeah, half, right? Okay, that's the results. Okay. I believe we need more example and more practice to get you to be more familiar with this. So please check later the exercise, okay, the exercise that I planned. Okay. Okay. After this, we are going to move on to the volumes. Okay. Okay. Hello everyone. So this is additional content for supposed to be your class on November 30th. So after we discussed last week on the area between curves and some examples, and of course you also getting some assistance from your TA. I will start our class today by taking the applications, the other application for the integrals. That is, we need to find the volumes. This is actually 6.2, so the volumes. So we can think the volumes with the type of solid. So we start from this cylinder. Okay. So cylinder, like we take some element of cylinder as this tree shape. Okay. So we can have, for example, say we have the cylinder V equal area multiplied by the height. So cylinder is typical. If we want to find the volume of cylinder, we take this the area, the base area, and multiply it with the height. Okay. And it's also true for most of cylinders, like in the second one here is the circular cylinder. We have the pi r squared, the base, and multiplied by height. And if we have the supposed to be like box, we have the area that is the length and width and multiplied by height. So all these three, they have the same common that the volume will be the base of the area multiplied by its height, right? Okay. Now imagine we are having some solid in our two dimensions space well, if we try to take our picture, let's imagine that there's one solid. Okay. Let's say this solid is A. Okay. And this 3 dimension. Okay, so imagine this x, y axis is in two dimension space, and we have a 3 dimension shape above this x-axis. Okay. So it's like, well, if you would like to make sense, maybe it has 3 dimension. Maybe z is there. Okay, to make this make sense. Okay, and then imagine the cross sections within this solid A. So let's say we have a cross section that we cut and make A of x a function. Okay. So A of x is a cross section of the solid. Okay. And then what we are doing now, when we cut, then let's try to cut with other interval, with some intervals. Okay. So let's cut so let's say from A to B, we are cutting more and more cross sections. Okay. And we could see, let me put the picture. This is the illustrations. So let me take this. So imagine like we are taking the space with width of the delta x, okay, with this interval, and then we take for some n, like this is similar to what we have in the rectangle in the Riemann sum, but this is in 3 dimensions. So we take this and we cut the shape becomes several. Let's say this is, we call the slabs. Okay, the slabs. So we have several slabs between interval A and B. Okay. Now we can think the volume of the slab let's say the S. SII means the how many the cut will be. This is approximately is area of the cross section, right? Multiply with the delta x. Delta x is our height. Okay, so this is the area. This is the height. Same principle as we begin our talks. Let the area and height. Okay, and then we could approximately estimate this volume using our summations, starting I from 1 until some n of this equations. And if we take the n getting infinite, then the approximations will be going to be better. Okay, and you can think the slices becomes more thinner. Okay, so imagine that we are having more cut. Okay, imagine that the cut. So imagine cut is getting thinner. So of course, if the cut is getting thinner, then the approximation will be getting close to the real volume that we want to approach. Okay, so we define this volume when we take the limit as n getting infinity, as usual in the I think in the previous Riemann sum. So we can take this as our definition of volume. So we can have our solid that lies between the interval A and B. And if we have the cross-section area in some plane, we call the plane PX, that is actually what we have here. This is the plane here. Then the definition will be the volume will be limit as n approaching infinity of our summations of the cross-sections area multiplied by the delta x. And we could define this as in our integrations from a to b of ax dx. Okay, now to get this in more concise and clear review, let's imagine, okay, we know the sphere, right? The sphere, if you remember, the volume of sphere is pi over 3 pi r cubed, right? Now, if we imagine this from the integration perspectives, then we could start with imagining the cross section of the sphere. So let's draw in the new page. If you want to take notes on this part, you can pause the video and take notes. Okay. So let's say we have this sphere. So we begin with this sphere. And then we could take the cross section here, the red color one here. So we take so we naming some variables that we might need. So variables like r in this sphere, and then we take some points. Okay, we take some points. Let's say we take at some points that when x here. Okay? So we say that this is x. Okay, this is x. Okay. This is x, and this will be y. Okay. So we name x, y, and r. Okay. So we could make some definition from the triangle that r squared is y squared plus x squared, and we could take the y as square root of r squared minus x squared. I will take the positive one. So it's supposed to be having plus minus, but since it's going to be the volume that we want to approach, then we need to take the positive one. So then, well, you could also take the negative one. Well, it can be negative, but let me just take the positive one, which means the positive one is the above the x-axis, right? Okay. Now cross section area, or we take we take the cross section as a of x. This will be the area of the circle. So we have the circle, the red circle, that is a circle with radius y. So we could write pi multiply with y squared, or we take y squared as r squared minus x squared. Okay. So I don't think the positive negative will make some differences in our calculation, because we will square those two. Okay. And then we take the the a is from negative r and b is r. So what we are going to do is we are going to take, like, imagine we are having a lot of cuts here. Okay, we have a lot of cuts, and we imagine that the cut itself, the height, it means because the cut will determine how the height will be, the delta, right? The delta x. So the delta x is actually our dx, right? So we could imagine that the delta is really small, and that is our dx. And we could think the a and b is our negative r and r through this description here. So we could write that the volume as our integration from negative r to r is multiplication of ax and then multiply with that with dx, the delta, the height. So we could write here that the a of x is pi r squared minus x squared and then dx. And remember, we have a symmetry in our integrations. This sphere has a symmetry, right? So we are sure that we can make this becoming 2, and then this will be 0 to r, and I will move pi to outside because it's constant, and this will be r squared minus x squared dx. R squared is actually a constant r, so we could take that as our constant, and we integrate. I think we can directly integrate this, becoming r squared x, and this will be x cubed over 3, and plug in 0 and r, and we subtract these two. So r cubed minus r cubed over 3 minus 0, right? So we have now r cubed minus 1 over 3 r cubed is 2 over 3, right? 2 over 3, so this will be 2 over 3 r cubed. So multiply with 2 pi, this will be 4 over 3 pi r cubed. And this is our definitive formula for the sphere, right? Volume of sphere. Okay, so we can prove the volume of sphere through these integrations, through the volumetric integrations. Okay, so that's one thing in the first part of definitions and to understand the volume. Okay. Now, the second part of the volumes is what we call the volume of solid revolution. So this can be done when we if we have, or if we revolve a region about a line, then we will get the solid of revolution. So imagine that we have for example, we draw the, let's say this is y equals square root of x, okay? And let's say we are going to take the region, let's say from 0 to, let's say 1 is about here. Let's say 1 is here, okay? So if we rotate this curve, rotate about the x-axis, so x-axis is this part here in the bottom. So we are going to rotate this, okay? So imagine that this is going to be rotated through there, and you will get a shape that is a thing. You could imagine the shape like a bubble or like a vase in a flower vase, right? So you could have this 3D three-dimension shape that we call this is a solid of revolutions. Now the same thing what we did in this in the sphere in the previous page, that we are going to take a look at our cross section here. That our cross section, maybe we can take cross section more in the middle. Let's say take here. Oh, I think we just need to take this from 0 to 1. So let's take the in the middle here. Okay. So let's imagine that the radius of the circle, the green one here, is this y, right? This y, and this part here x, and we know that y is equal to square root of x. So we could start with a of x is pi multiply with square root of x squared, or we can have pi x. Okay. Then the volume will be start from 0 to 1 of ax dx, and this will be equal to pi x dx, and we could take the integrations, and x become x squared over 2, and we know that this will be equal to pi over 2. Well, if you want to see more clear picture on this, you could see that this is what we have. So we take some so we take the delta, so the delta is this. Okay. So this will be the delta x, or the dx, okay? And then we rotate through the x-axis, and we have this as our illustration for the part that we are going to approximate, and then we take the integrations, okay? So this is the r, right? Or we could take this as our y, and then we multiply with the height, which is the delta x, or dx in our integration. Okay. Okay, so I think it's going to be really direct for the volumes. Okay, another examples. Find volume obtained by rotating y equal x cubed, y equal 8. I think not really, maybe going here. Rotating a region bounded by this whole line and the curve, okay, about y-axis. This is the center of the rotations, so it's rotated about y. So first thing, my tips, also my I think the general advice in these sections is somehow or sometimes you need to draw the sketch of your integral, not really like a good sketch, just a rough sketch to imagine how it looks like and how you can define the cross sections. Okay. Now let's say that we start from here is the y equal 8, and then we have the y equal x cubed, is going to be, let's say we have the hair, right? That let's say this is our y equal x cubed, and then x equals 0 is just the, so this is y, this is x. So x equals 0 is just the, let me use the green color. So this is x equals 0, right? So this is the area. And then we can take our times to see the rotations is on y-axis. So what we need to take is we take this small area and we name this like it's the dx is over there, or for now it's not dx, it's dy. So to solve this, we need to exchange all the x into y. So we are going to take the x as function of y, but the idea is still the same. So what we have, if we take the better picture, this is the better picture. So what we are going to take is we are going to take the cross section, which is pi multiplied with x squared, right? So this is the x, this is the y. But since we are going to have a function of y, then this will be equal to square root of our cubic root of y squared. So we have pi y of 2 with power of 2 over 3. Okay, so that's the circular of our cross section. And then we are taking the integrations from 0 to 8. So we are taking the integration from x equals 0 to, or y equals 0, because x, when x 0 is y 0. So from y 0 to y equal 8. So we could take this and we multiply the a of y dy. Or we could write, and we take the integration as usual. So 2 over 3 plus 1 is 5 over 3. So we'll have 3 over 5 y with power of 5 over 3 and plug in 0 to 8. And if you take some time to solve this, you're going to see 32 multiplied by 3 is 96. So 96 over 5 pi. Okay, so we can do the dy, okay, and we can do the dx. So this one we are taking dy, okay. The previous part we are taking the where's the previous power here? The previous part we are taking the dx. Okay, so it's not always going to be all with dx, but we can also take approach and make it into dy. In some cases, we can make it by both of them. So both of them will have the same results. Okay, either you are using dx or dy. Okay. Like usual, in the area between curves, sometimes we are going to have some region that is we are not sure how the endpoints will be. For example, region, let's say region R is enclosed between y equal x and y equal x squared and rotated about x-axis. Find the resulting volume. So to understand the question, we are going to take some time to draw the sketch of our graphs. So let's say we have the y equal x, maybe over here. That's y equal x. And let's say we have, well, we could take that there. Let's say this is y equal x squared. Okay. Yeah, let's say that's our x squared. And then we could think the intersection that we are going to do to describe, okay, because of the questions. So we are going to describe that the intersection is when x squared is equal x, or x squared minus x is equal 0, or x is x minus 1. So x equals 0 and x equal 1, this will be the intersection. Okay. Then this will be 1, this will be 0, and this will be 1, 1 to be precise, and this will be 0, 0. Okay. And then we need to take this and rotate about x-axis. So we take this, our differentials, or our dx, right? And we are going to have like a disk, right? Like a disk having a hole in the middle, right? Okay, I hope you can clearly see what I'm drawing here. So then our volume will be, okay, or maybe we could start from the cross sections. Okay? Maybe I will give you the results, maybe directly writing the picture. So you see the disk is having a hole inside, and we're going to see that the hole is well, if we take our time to see that this one here is x squared, okay, and this one here is x, right, from here. So this one here is x, y equal x, right, and this one here is x squared. Okay, now we could take the cross sections as pi x and then squared minus pi x squared squared. So we have pi x squared, or we could have pi x squared minus x with power of 4. This being the outer radius, and this will be the inner radius. So the volume will be from 0 to 1 of ax dx. And then we can just take our time to integrate. And this is just 1 over 3 minus 1 over 5. Okay, because the 0 will be 0. So we have 2 pi over 15. Okay. So we could have also a consideration when we have a hole in the cross sections, okay, which means we are going to take the curves, especially when we have the region between the curves. Then we are going to imagine which one of the curves that is on the top and which one is on the bottom. Is this precisely the same or similar with area between curves, okay, that we have introduced at the last week's classes, right? Okay, the same, if we have the same problem, but we are going to take our approach to rotate the same problem here. Let me copy all this part. So same problem we copy, but we have this different rotations. So let's say we have so let me erase part here. Okay. So what if we take, so let's say this is 1, this is 2. So let's say we have y equal 2. So if we rotate region about y equal 2, so the y equal 2 becomes our center of rotation. So this will be, so let's take our time to, well, suppose that we have like a mirror, okay? So we are going to have, for example, if taking here, and if we take a mirror like that, so perhaps this will be the cross section. Okay. And then how about the radius? What will be the radius? So the radius, we could start looking at, if we take the radius like that, or maybe let me just getting the picture inside. So this is the picture. Okay. So what we have here, we are going to rotate this region here about this y equal 2. The implications that we are going to have the cross sections with a large hole, if you see here, that we state also, okay, we still state the radius, okay. So the outer radius is from this part here. This part, like x squared, is from this one. If you can see that the one on the bottom is the x squared, and the one on the top here is the x. So so the outer is 2 minus x squared, and the inner radius is 2 minus x. So the cross section, we can start from the cross section, is pi 2 minus x squared minus pi 2 minus x squared. So this will be outer, this will be inner radius, right? So the volume still ax dx, and this will be 2 minus x squared and then minus 2 minus x and then squared, and then the x. And somehow we need to expand this and solve. Okay. And then we say that we have this x power 4 oh, this is supposed to be 4, sorry, 4. So negative 4, yeah. Okay, so negative 5 plus oh, this is also 4. Yeah. So plus 4x, and 4 minus 4 is 0, so we just have this. And then we take the integrations as usual. So we take x5 and plug in 0 to 1. So we have 1 over 5, 1 over 5 over 3, sorry. And then plus 2. So this will be equal to 8 pi over 15. Okay, so I hope you get more understanding within this volume. Okay, now what we have done in within these sections, we call this method as, usually we call this as a disk method, or when you have a hole, we call this a washer. But the name is not really that important. Okay, as long as you know how to find the volume, and it certainly have a shape like a disk, right? So that's why we call them disk method. Okay, so let me give you some examples on some parts. Okay, so to get more understanding on this volumes. So let's say we have these two questions I give you. So find the volume of the resulting solids that you have the region, and you rotate about the y-axis, both of them y-axis. So let me get through that part. Okay. So you can take some time to check, and you can pause the video and then solve by yourself. But let me go through for the first one. So you can take this. So as usual, we take our sample like that, our rectangle. So this will be dy, right? So we are going to evaluate in terms of y, which means that we are going to take this, and we are going to have this as our x. Okay. Now the cross sections, or if you were already familiar with the integration, we can just take our volume and then integrate from 1 to 9 of the a of y dy. And a of y is the cross sections is the pi r squared. The r is this x, or this cubic root of y minus 1. So we take that pi and then y minus 1, and then squared becomes 2 over 3, and then dy. And then this will be pi 3 over 5 y minus 1 5 over 3, and plug in 1 and 9. If we take 1, this will be 0, so no problem at all. So we take pi 3 over 5 pi, and then 9 minus 1 is 8. 8 cube is 2. 2 with power of 5 is 32. 32 by 3 is 96, so this will be 96. So 32 minus 0, this will be 96 over 5 pi, right? Okay, I think not too crazy for the first one. Now how about the number 4? Number 4 is the same rotations about the y-axis. So what could be is we take this small rectangle here as our sample. This will be dy, and imagine that we are going to have the cross sections with a hole, or we call this a washer, not a full disk. Okay, so first let's determine our cross sections and the radius in the cross sections. So we are going to have dy, right? Our integration will be in terms of y, which means all the terms, we are going to take this into y. Okay, so take like that. Okay, and then the red line will be the top radius, or the outer radius. the blue line, the blue curve is our inner radius, right? So we take this is inner and this is outer. So our cross section is outer minus inner. We can write cross section pi, and then the red line is the 2y squared minus 2 over y, right? So we have 4y squared minus 4 over y squared. And the volume, now we take the y from 1 to 2, okay? And then we take the cross sections and then we take the integration as usual. And the 1 over y squared integrate is negative 1 over y, so it will be plus 4 over y. And then input 1 and 2. So this will be, when input 2, it will be 8, 32 over 3, 32 over 3 plus 2 minus 4 over 3 plus 4. Okay, so we can check the results. This will be 38 over 3. 16 over 3, it is 22 over 3 pi. Okay, so not a problem, not really difficult, I think. Let me give you another questions and see how you can solve this. So find volume of solid by rotating region bounded by given curves about the specific line. This is usually a typical question. So what it means is you will have a region bounded by some curves and you will have some rotation rotating about specific line. So for example, the first case that I need to give you, and let me check first. I will give you the okay, when you have y equals square root of x minus 1, y is equal to 0, x equal 5, about x-axis. And then okay, b is y equal x cubed, y equals squared x, about same x-axis, and then y equal x squared, x equal y squared, about y equal 1. Okay, these 3 questions. So try to solve this. Pause the video and then try yourself first, and if you're ready we can start to discuss. Okay, so let me make the gap between these questions. Let me take the gap maybe here. Okay, I think the first one is not too difficult, it's pretty simple. right? It's supposed to be pretty simple. So first, maybe you need to sketch. Okay, can you sketch this curve? Well, you could imagine y is square of x. This is easy, right? Square of x is easy. But then you need just to take the inside, change to x minus 1, which means we have a transformation. Okay? Remember transformation from the very first chapter in our calculus. So we have, now when we have x minus 1, that means we have a square root of x and then shift it 1 unit to right, to the right. So let's say this is 1, and this will be our curve. So the same curve as square root of x, but we shifted 1 unit to the right. So this will be y equal square root of x minus 1. And then we have the y equals 0, which means it's the x-axis, and then x equal 5. So 2, 3, 4, 5, maybe 5 is here. So let's say this is the x equal 5. So this is our area. And then we are going to rotate about x-axis. So this will be our rotations. Then we are having, this is our rectangle, this is the sample, right? And then what we need is, we need to check the cross sections. So this will be our disk, right? So the disk will be volume from 1 to 5, ax dx. And we have the ax is square root of x minus 1 squared. So pi x minus 1, we have already squared that, and then dx. And we have, so half x squared minus x from 1 to 5. Okay, calculate a little bit. So we have 25 over 2 minus 5 minus half minus 1. So 15 over 2 minus half. So plus half. So 16 over 2 is 8. So we have 8. So 8 pi. Okay. I think not too difficult. I think quite simple. Try the next one. Let's try number B. Okay. You can pause the video, and if you want still to try to check. Okay, now we can start with the sketching graphs. That is, I think, quite easy. So this will be y equal square root of x. And this one here is the x cubed, y equal x cubed. Then we need to rotate on x-axis like that. So we take, perhaps this is our samples, but before we move on, we need to make sure that we know our intersections. So we take x cubed and square root of x, they equal, like let's make it equal. And of course we can we could see that we might have this problem. Then, or perhaps we could take the, let's say this is our function. Well, we could take the the derivative and take it equal 0. But I don't think it will solve the problem. So maybe, well, we could imagine like when x is equal 1, I think this will be the faster choices. Then we could see that it will be getting 0, right? So x equal 1 is our zeros, and also x equals 0. This is also our roots, right, in our polynomial. Okay, we could, I think it's convincing. So this is 1 and 0. So the volume, so we could say that this is from 0 to 1. This is a of x dx, and a of x is pi. The outer radius is square root of x squared, right? Minus square root of, oh, not square root, it's x cubed. X cubed squared, okay? And then dx. And this will be x minus x with power of 6 dx. And this will be half x squared minus x over 7 with power of 7. And then plug in 1 and 0. And 0 will be 0, so we will consider 1 over 2 minus 1 over 7, which is, we take 7 over 14 minus 2 over 14 is 5 over 14. 5. Okay. Now the third question, this is quite still, I think still okay. You need to be more careful on this one. So let's say we have we need to confirm the intersections. Okay. First is we have the x squared, which is, I think, easy to imagine. This is our typical x squared, like that. And then we have the y squared. It's actually the same thing as x squared, but on this side. So this actually, the region is in between. Okay, so this will be the region. That region, right? So we take our sample because we are going to, oh, wait a minute. We need to rotate to y equal 1. Okay, so y equal 1 is, well, we need to convince ourselves to make sure that we're having the same with x like that, and this is square root of x. And since it's similar to what we have in the previous questions, it's similar. So the only way we know the intersections, then this will be 0 and 1. So this will be 1, 1. And this is also where the y equal 1 is will be our center of rotations. So we are going to rotate. We are going to rotate this region, rotate to this y equal 1. So we will have okay, that's our cross sections. Okay, now the inner radius will be this, right? Inner, I think too complicated. Inner, and this part here, this will be outer, right? So we can take our times to imagine the cross sections. Outer minus inner. So outer will be the x squared, or in our case, this is going to be, so this is y equal 1, right? This height, y equal 1. So we want to have this height. We know this curve is x squared. So the outer is 1 minus x squared, right? Okay. So this will be pi 1 minus x squared squared. Okay. And minus, then we need to make this y in terms of x, right? So the inner is the square root of x. So that means 1 minus square root of x, okay? So it's 1 minus square root of x and then squared. And then we need to solve this first. 1 minus 2x squared plus x4 minus 1 minus 2 square root of x plus x. And we get this minus x. Okay. Okay, now we could take the volume and then just integrate all this stuff. And then plus 2 has become 4 over 3, because 2 over 3, and then x 3 over 2 minus half x squared, and then from 0 to 1. And this will be 1 over 5 minus 2 over 3 plus 4 over 3 minus 1 over 2. So 2 over 3 is taking to 5 is 10 over 15. Taking to 3 over 15 plus 10 over 15 is 13 over 15. And then minus half. Taking 15 is 15 over 30, and this is 26 over 30. So 26 minus 15 is 11. So 11 over 30 pi. Okay. So I hope you get the idea. Okay. We'll give you more exercise. Okay, and we can skip to the next sections. And make sure you check the exercise. Okay. Okay, the next part of this lesson is we're going to see, okay, because we know that we can find the volume through integrations through this method and the or washer if you have a hole, then what is other method that we can also try to use to find the volume? Okay, for example, if we take some times to check this integrations, okay, so we take the curve, this is the curve, this is the curve, and we are going to rotate. Okay, we are going to rotate through the y-axis. Okay. So the blue curve here, or the blue area, is the region that we want to rotate through the y-axis. When we try this one, and we are going to have some confusion because the curve itself is just one curve. So when we have, for example, the same situation like before, we want to take the inner radius, the outer radius, but the curve is the same. So how to make the inner and outer radius? Okay. So this problem cannot be solved through this method. So cannot be solved through this method. So we need to come up with a new method that could be generalized and that could be also, especially for this type of curve, we could solve this. Okay. We call the method cylindrical shell. So as the name suggests, that we are going to observe a cylinder and then take a look at each part. So let me introduce you to cylinder. This is the cylinder. So this cylindrical shell. So let's say we have like a can, or well, we say the cylinder with some thickness. So the thickness is the delta R. Okay, and you have the R1, R2, and we have the R that is this is the average R. Okay, and we have the height. Okay. Now, the volume of cylinder, as you remember when we dealing with the volume at the beginning, the volume of cylinder is just the area multiplied by height, right? So we could see from this part, we can imagine this like a cylinder with some thickness, some hollow area, that we could think this is as V2 minus V1. V2 is the cylinder with radius 2, and V1 is cylinder with radius 1. Okay, so R1, R2. So we could describe this, and this will be R2 squared H minus pi R1 squared and H. Okay, the area and then height. Okay, and then we take pi and H out the equations, and we see that we have this now. And then we can factor this part. We can factor out. Okay. And then if the delta R is R2 minus R1, and the R average, this is average, is half of R1 plus R2, then R1 plus R2 is equal to R average, then the volume we can write down as 2 pi R2 plus R1 over 2 multiply with H, and then R2 minus R1. And this will be 2 pi R, H, and delta R. Okay, so this part here is the R, and this part here, the R2 minus R1, is going to be delta R. Now this volume here is a new approach for us to try to solve the problem in the first picture here, the first graph. Okay. We can also take a look at this volume as the 2 pi r is the circumference. Okay, this is height, and the delta r is the thickness. Okay, we can remember this within this keywords. Now let's say we observe in a more analytical way. Let's describe in more details. So let's imagine that this part here, okay, we are going to rotate on y-axis. Okay. So imagine that this curve will create a three-dimensional shape. Okay. And when you try to take that shape, it probably looks like this. Okay. So then of course we have the interval from A to B, right? And then we take these intervals, we divide into n subinterval. So we cut into pieces. Okay. And then this is pretty similar with what we've done before in the early introduction of volumes. So when we cut into pieces, we can imagine that this will be our pieces. So let's say we try to define, the intervals a, b into subinterval. Okay, so we divide into this subinterval, and then we can see that it has certain shape. When we increase the number of n, the subinterval, if we divide into more and more pieces, you will see that it's approximately getting closer to the real shape that we have, that we need to have, okay, from the question here. So we want to approximate using this shapes, okay, within these subintervals. And then we could write some equations to relate those things as for volume I is for the how many interval we have. So we could have 2 pi xi and then f of x and multiply with delta x. So this is actually how we could rewrite the 2 pi r h delta r. Okay, so the height is f. Okay, so this will be the f. So the height, this is height. This is a delta r. This is 2 pi r, the circumference. So what is the r? Okay. The r is actually the radius on this, or maybe this. So the radius is here, and this will be the height. And the delta is just a small pieces like that. This is a delta r or dr later, okay? And then approximately we can write down in terms of summations as usual when we try to define the integral. Okay, so if we let the n is getting infinity, so we take the definition, and we get the integration from a to b 2 pi x f of x dx. Okay. So the volume, let me write the conclusions. So if you want to take notes, you can pause the video and take notes. Okay. But what I want to focus on is that this method, which we call the cylindrical shell, so V is 2 pi x f of x dx, where 0 is less a less b. Well, we could take this as breakdown. What we take this into several parts to make sure that we understand what it is in terms of practice, in terms of the applications. So this is thickness, this is the height, and this is the circumference. And we could also take this approach into more easy visuals like this. So if we cut open this shape, so we cut open here, and then we straighten the shape, we have this structure, right? And the volume is 2 pi x f of x and delta x. We'll multiply all, right? The volume of the rectangular shape here. Okay, that is actually true, right? So it's the same. So I think it's better visuals to illustrate how the cylindrical shell can be also understood, right? So now back again with the questions at the beginning. We need to calculate this, right? We need to focus on finding the volume. So within the method, then this function here is the height, right? And the radius that we need to take into the circumference is we can take this as our radius. Okay. And what is this? We can take that as our r or x in terms of our functions now, our curve. So we can take this as x, and we can write, if you want to calculate from 0 to 2, then 2 pi x, okay? And then f of x is h, the height is 2x squared minus x cubed, and then the x. And then we solve that. We take out 2 pi outside. And we need to compute the other x into the equations. Okay. And then we take that, and then 8 minus 32 over 5. And we get that this will be 16 over 5 pi. So we could try this method to solve. And then, and actually, cylindrical method can be applied for all condition in our case here. For most integration volume problem. Okay. While the Dijks method, it has restrictions, such as this kind of example. Okay, I hope you get the basis of understanding for the cylindrical shell, and I think we need more practice, okay, exercise to get into the idea. Okay, maybe one more example. Okay, one more example to understand this method. Okay. Okay, find volume of solid obtained by rotating about y-axis the region between y equal x and y equal x squared. Okay. I think this is the same as we did before in the volume, but we want to make sure that we can solve this within this cylindrical shell. So let me draw again the sketch. So this is y equal x. And this will be the y equal x squared. Okay, so we are going to rotate through y-axis, which means here. So usually, if we take this, and we are using the x, and this is just a normal this method, right? But we are going to take the cylindrical shell, which means when we rotate this, we want to make this sample. What we are going to take is we are going to make this into a cylinder. Okay. So the height, we see the height. The height is this, right? This is the height. Let me write with the just taking just h like that to know to take to denote that this is the height. And the height itself, if we see how it looks like, so the h is x minus x squared, right? This is the height. And how about the radius? Okay, the radius is just this radius, right? This is the radius. Well, we could say the radius is on the x-axis, so r is just x. So we could write that the volume from 0 to 1, remember this is 1, 1, this is 0, 0. So from 0 to 1, so 2 pi x multiplied with the height is x minus x squared, and then the x, okay? And then 2 pi, and this will be x squared minus x cubed, and the x, and this is supposed to be so 1 over 3 minus 1 over 4 is 1 over 6, 1 over 12, yeah, 1 over 12, so we have 1 over 6 pi. You could check with the disk method if you want, how it looks like. Okay, and then from here you should be able to tell how to use the normal method, the disk method, or the cylindrical shell.